All right, this is the uh, fluid dynamics and solidification analysis for my um, mold that I sent to VoxelJet for uh, Lokensgaard's PDD 212 class. I just finished up the simulation, so let's watch through. I set it to 10-second fill time. It's kind of annoying how much it's splashing right now. I don't think this is actually how it would be. Um, I think part of it is up here, as you can see, my sprue in the software is significantly smaller than my sprue in the actual part. Um, and I'm pretty sure that isn't helping anything. Can I move it while it's playing? Yes, I can. It's just very slow. Good God. I wonder if it's rendering through my processor. That would make sense. Um, so as you can see, it fills up. It goes through the sprue. It fills up the runner, and it starts to go into the gates. The end gates are kind of messy. The flow isn't as lamellar as we'd like, or laminear, whatever the term is. However, in here the flow's not bad. It looks fairly steady. Um, it makes me wonder if I might have been better off doing two separate systems of just four instead of one system of eight. Because you can see, like, it flows fairly well. There's definitely going to be some air bubble trappage there, but that's whatever. That's to be. I don't want to say it's to be expected, but it's mistakes happen. This is a learning process. Um, okay, so that's the basics of how it's going to fill. Looking at the solid fraction, so it looks like the actual dice itself should be good, which kind of surprises me given the air that we have in these top corners. Um, or theoretically would have. I'd expect there to be some more fill issues here. We start to see that going into the sprue and the gates in the runner right by the sprue, we have some solidification issues or like some issues with it being solid all the way through. That's honestly not too problematic because that's all going to be scrap anyways. The gates are going to have to get snapped off and the dice sanded down for finishing. So anything up here not being solid isn't a huge deal. Velocity, I this I'm guessing this data didn't go through properly because this tells me nothing. Unless I meant to play it, which isn't going to happen. Last air. Okay, so this is interesting. So earlier we talked about how I expected in the corners of the dice we'd be seeing some air pockets. It actually looks like in my runners I'm going to see some air pockets and then a bunch of air pockets up in the sprue. The air pockets up here, I'm genuinely not at all concerned about. They don't. They're not going to affect the end result of it too much because, like I said, that's the sprue that's all going to be discarded. It looks like all of the other air pockets we have are also going to be like in the runner. Like I don't see any of them in the actual dice. They're all in the runner. So that's perfectly acceptable. Those are acceptable margins of error. Those are the places I'd really prefer this stuff to be, anyways. Um, no mold. Oop. Okay, so we're gonna get a little bit of mold erosion right at the bottom. That's to be expected. We're pouring molten metal right into it. But we're not going to get any other mold erosion. So what that tells me is if I could redesign the dice to either not have the nubs or even just change up the manufacturing process so that those nubs were drilled in rather than cast, theoretically we could turn this into a production scale system to making dice. Theoretically. Pressures, okay. I don't fully know how to interpret this. I'm kind of surprised not to see a spike in pressures around each of the individual nubs. However, this does seem to make sense. There'd be the most pressure at the very bottom, the least at the top. There's a little spot right up here that I don't really know what to make of. But again, it's in the sprue, so it's not extremely critical to the end quality of the mold. Fill time, oof. Oof, 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 oof. This is ugly. This is absolutely ugly. So the middle dice aren't bad. What I'm looking for in the middle dice, from how I understand how this works, is you want it to be a very smooth, very even transition of colors. So you see, like, on these two middle dice, and even this third one, it's a very, very smooth, like, green to yellow to orange to red. Like, there's bands, but they're not too bad. And even on this side, you can see in these corners, it's pretty smooth. But a couple of these dice have some really awkward corners where the fill time to the rest of it is very sharp. I can see that causing a lot of problems with fracturing, a lot of problems with filling in properly, with air pockets getting trapped. I'm going to ignore the issues in the runner and the gate system. Like, as you can clearly see, there's a lot of odd sections in the runners and the gate, and I think something I could have done better to help prevent it is on the gate here I have these angles. The angle was put in, it was from one of the pamphlets we read in class, but I think I either needed to do a steeper angle or a more shallow angle because it looks like what happened is it broke on, like the flow of the metal broke on the angle and splashed up and in. And when it splashed in, it created a very uneven and differential kind of fill. So that's something we could cut down in the future. Cold shuts. Okay. Oh, there's one. There's two. So it looks like there's two in that dice and none anywhere else, which I call a fat BS on. We all know that's not how this works. If there's cold shuts in one dice, there would be symmetrical cold shuts among at least the other dice on that side. That is good to note. I was kind of expecting this when I was thinking about the metal flowing over the nubs, and it looks like my suspicions are correct, because let's zoom in on those for a second. You see, okay, one cold shut is kind of away from it, but that's also where this one would have been the metal would have been splashing into the mold. And then there's one down there by the nub, so it's not great, but it's to be expected. It was expected and predicted when I was originally setting this up and thinking about it. Mold temperature, this, okay, so it shows me the actual mold. Yeah, that doesn't surprise me. I don't know how else to look into this, so I'm not too worried about that. So that's our filling analysis. Let's go over to solidification real quick. Okay, so we're going to have temperature. Temperature on everything looks good. The sprue's obviously going to be a little bit hotter. That makes sense. Solid fractions. Again, I don't see anything too worrisome. Solidification time. I'm curious why I don't have a solidification time on the dice, especially seeing as the full analysis is done, so I should be able to see a solidification time. However, it's also possible. Oh, it's clear, so it solidifies immediately, which is concerning and not at all how this would work, but whatever. And then yeah, that's understandable. Microporosity. It claims that the analysis was done for solidification, but it's very much looking like it just kind of quit. Because we've only got this nub here, unless that's saying that's the only spot that would have microporosity, which is to be very much expected that there would be that spot would have microporosity, because that's the sprue. Ideally, we're going to fill all this up, and then as the dice shrink in that, the extra metal from the sprue will go into the runner and then into the casts. I don't know what this means, but it looks good. I like when everything but my runner and my sprue are uniform. We didn't cover Niyama when we brought the guy in to explain this, but yeah, it looks good. I like it. Pipe shrinkage, I don't know what that means, but I don't see any of it. Solidification modulus. Okay, I see what this is saying. This is saying that this is the nub that's going to kind of sink as this all sets and solidifies. We've discussed this already. That's to be expected, and it's actually kind of acceptable. Like, it's the sprue. If we are going to have to control for shrinkage anywhere, we want to control that shrinkage to specifically that spot, the sprue. Porosity, again, we're looking at almost identical situations with that, which I'm perfectly okay with. Total shrinkage volume is almost spot on with all three of them. So yeah, and then mold temp, again, useless information. I think the big three to look at are the solidification modulus, the porosity, and the shrinkage volume. We're seeing a very, very consistent pattern of this space up at the top of the sprue, or I believe that would be the pore cup. That space up there is going to have some major shrinkage. The thing is, though, I kind of designed it that way. When I was putting this together, part of the reason I gave it such a long sprue and such a big pore cup is I wanted there to be that extra metal in the mold to fill in as it shrunk, as the aluminum cooled. And so if that's where we're going to get all our porosity and shrinkage, that's totally fine by me. Um, so yeah, that's my analysis of the simulation of my dice mold. Um, yeah.